The universe began nearly 14 billion years ago, an event that we call the Big Bang.
Remarkably, just 2 years ago, the Hubble Space Telescope detected a peculiar point of light within its view, igniting the interest of astronomers. At first, scientists could scarcely believe that this seemingly trivial dot of light was actually a massive galaxy situated at the farthest reaches of the observable universe. It was only when the Webb Telescope focused its sophisticated instruments on this mystery that its actual nature became apparent. Observations from Webb revealed that this point of light corresponds to a primordial galaxy known as GZ9P3, which is surprisingly more massive and advanced than anticipated. Located at a redshift of Z equals 9.3, GZ9P3 provides a window into the universe's early history, specifically just 510 million years after the Big Bang. While astronomers have previously identified other galaxies that emerged around 300 to 500 million years after the Big Bang, none have shown the significant mass that GZ9P3 possesses. These findings suggest a need to reconsider the processes of star formation within the galaxy, implying that stars must have been formed at a much quicker rate and with greater efficiency than previously thought, to allow GZ9P3 to attain its impressive size in such a brief cosmic duration. Moreover, GZ9P3's peculiar shape presents an exciting avenue for uncovering the universe's early secrets. The research team noted the presence of two luminous patches within the galaxy, suggesting the existence of two closely packed nuclei. This feature strongly indicates a galactic merger, an event where two primordial galaxies collided during the universe's infancy, a scenario that could provide insight into how galaxies evolved in their formative years. In addition to mapping the age, mass, and structure of this ancient galaxy, the researchers employed the JWST to probe its stellar population, discovering a dominance of young, luminous stars contributing to GZ9P3's striking visual characteristics. Further analysis revealed the presence of specific elements like silicon, carbon, and iron within the older stars of GZ9P3. Iron, notably, is the heaviest element that stars can synthesize through nucleosynthesis. When massive stars ultimately exploded in supernova events, they released these elements into the surrounding space, enriching the early universe with metals that later became integral parts of new stars. Curiously, the abundance of older stars found in GZ9P3 suggests a more rapid chemical maturation of galaxies than scholars previously believed. This observation implies that stars enrich their surroundings with metals at a much faster pace than was thought possible. The unexpectedly mature older stellar population within GZ9P3 challenges existing cosmological paradigms, indicating that star formation and evolution may have occurred far earlier than previously anticipated to allow for this significant aging in such a brief cosmic duration.
When you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up. Something is literally accelerating material very fast across unimaginable distances.
These groundbreaking findings suggest a possible need for a revised model of galaxy formation, accommodating the rapid growth of galaxies to such a chemically mature state, alongside their remarkable mass. The implications also extend to the role that galactic mergers may have played in shaping the universe shortly after the Big Bang, highlighting their significance in the cosmic narrative. While our current cosmological framework is not fundamentally flawed, it appears that our understanding of the speed at which galaxies form may require substantial adjustment as the existence of these massive galaxies challenges conventional projections. Although cosmological models have been developed based on empirical observations and the theoretical foundations that support them, emerging data hints at a universe that is not entirely conforming to established expectations, a situation often referred to as the crisis in cosmology. This crisis arose when disparate methodologies for measuring the age of the universe began to yield conflicting results, a predicament that persists. The revelations from the Webb Telescope have further compounded this crisis, revealing discrepancies in our understanding of the universe's expansion. As galaxies continue to recede from us, astronomers utilize the cosmic microwave background radiation.
What if I told you that the source of the static, which we call the cosmic microwave background, or CMB, was the process that formed the first atoms in the universe almost 13.5 billion years ago?
The relic light from the universe when it was just 380,000 years old to calculate the rate of this expansion. The results have raised profound questions concerning our foundational cosmological theories and their implications for the origins and evolution.
When the Big Bang up to the time that matter and energy separates, right? That's 380,000 years or so.
Right.
That's still secure. There's nothing that's challenging that. So the work that Cobb and Turner did in the early universe book, even decades ago.
There's another technique where we know the expected brightness of distant supernovae and can compare it to their observed brightness. This comparison allows us to estimate the universe's expansion rate at the time the supernova occurred. When we utilize this method, known as standard candles, we can determine the universe's expansion rate, referred to as the Hubble constant. However, the difference between the results from two different methods is termed the Hubble tension, and this constitutes a significant issue in cosmology. Yet this isn't our only challenge we face now. A new cosmological problem has surfaced that confronts our models more than ever. When you gaze at the sky, assuming you're not in a brightly lit area, you see numerous stars. Among these stars, you also notice the Andromeda galaxy, appearing as a faint blur. This is because the universe is densely populated with stars and galaxies. The inquiry is what proportion of the universe is occupied by them. It seems like a straightforward question, but the answer is far from simple. This predicament arises mainly because existing cosmological observations contradict one another regarding the distribution of matter in the current universe. This conflict has led to the emergence of the enigmatic SA tension, also known as the new cosmological dilemma. The SA tension serves as a metric for the unevenness or clustering of matter throughout the universe. In simpler terms, envision the universe as a gigantic puzzle with pieces of matter dispersed throughout space. Researchers aim to decipher how this matter is distributed and how it aggregates. There are two approaches to measure this. The first involves accurately calculating it through low redshift observations such as weak gravitational lensing. Gravitational lensing occurs when the strong gravitational attraction of massive entities like black holes and galaxies functions as cosmic magnifiers, bending and distorting light from more distant objects that might otherwise remain unseen, yielding unique insights into the vast cosmos. However, the S8 value obtained from the second approach, based on the standard model of cosmology and cosmic microwave background measurements, does not match the values derived from low redshift observations. This inconsistency forms the confusing core of the S8 tension. So what is our next step? It is evident that there is a fundamental aspect that we do not completely understand. A missing piece does not align, despite numerous theories, observations, and hypothetical entities backing those theories. What is happening? In pursuit of answers, astronomers have employed one of the world's most advanced supercomputers to execute the largest cosmological simulations conducted to date. One cannot even begin to comprehend the monumental scale of the Flamingo project until you realize that it required an astounding total of over 50 million hours of computer processing time. This immense computational workload was distributed across the 30,000 processors that comprised the Dracalisma 8 supercomputer located in Durham University in the UK. Flamingo, an acronym for Full Hydro Large-Scale Structure Simulations, aims to perform all-sky mapping to enhance our understanding of forthcoming observational data from next-generation telescopes. What distinguishes Flamingo from earlier cosmological simulations is not only its vast size and exceptional resolution, but also its comprehensive approach that integrates factors beyond just gravity. Historically, most cosmological simulations have predominantly concentrated on modeling dark matter, which accounts for roughly 27% of the universe's total mass energy content.
In stark contrast, normal baryonic matter, which constitutes approximately 5% of the universe, has tended to be overlooked despite its potential significant influence on the distribution of cosmic matter at smaller scales. For example, phenomena such as galactic winds generated by supermassive black holes and the explosive energy of supernovae can significantly impede the growth of galaxies. Flamingo incorporates and meticulously tracks the behavior of ordinary baryonic matter, recognizing that while dark matter dominates gravitational interactions, the role of ordinary matter is crucial and cannot be dismissed in precision cosmology. Although the Flamingo simulations marked notable advancements like accurately replicating the formation processes of the Milky Way and Andromeda galaxies, among others, the project has encountered challenges, most notably in accounting for the observed weak clumping of matter in our present-day universe. This discrepancy represents a critical failure to address the very issue the simulations aim to clarify, known as the S8 tension. The implications of these findings may suggest that there are fundamental flaws in our current standard model of cosmology. Furthermore, Flamingo's results clash with the observations made by the Webb Telescope and other astronomical observatories, particularly regarding the spatial distribution of matter throughout the universe. Recent data from the Webb Telescope indicates that matter is still approximately 5% more clumpy than Flamingo suggests. This revelation supports the existence of the so-called Hubble tension, a persistent discrepancy in measurements of the universe's expansion rate. The Hubble Space Telescope's findings, now corroborated by those of its more advanced successor, the Webb Telescope, revealed that there is an exceptional inconsistency in the calculated values of the Hubble constant, which defines the rate of expansion of the universe. This situation presents a profound mystery for cosmologists, as not only do the measurements fail to align, but they also invite speculation about the existence of new physics that could elucidate the underlying causes of this perplexing contradiction. After eliminating measurement errors, we are left with the fascinating and thrilling chance that we have misunderstood the essence of the universe. Emerging theories are gaining attention, with some suggesting that dark matter should be dismissed altogether. I'm curious to hear your thoughts. Please share your comments and remember to subscribe.